Well, how'd you do with the mechanism? I'm hoping that you all gave it a good try, because that's where the answer is going to go. We're going to answer this question that we left off on. What makes a group, such as methyl, which is what we had in the previous problem, on toluene, an ortho-para director? So remember that if we have toluene and if we brominate it, the ortho and para products dominate over the meta product. What makes methyl an ortho-para director? We're going to see it's something that a group that can increase electron density of the benzene ring. In other words, electron donating groups are ortho-para directors. Okay, we'll flesh that out. But let's prove it first. So the mechanism has to show how this is true. Okay, so that's what the next page is devoted to. All right, so remember a few things first. When we've shown this mechanism before, and now we're going to do it in great detail with a group on it. Last time we did it with benzene. So remember that when we have electrophilic aromatic substitution, we form a carbocation called the sigma complex. So there's at least 3 carbocations we can show, right, that delocalize around the ring. Also, it's really important to remember some fundamentals. When we have a carbocation, that is our rate determining step of the reaction. Okay, so when you could stabilize the carbocation, you can make the reaction go faster. Rate determining step, RDS. All right, so since we've drawn this mechanism more than once, we're not going to show every detail. However, we are going to show the important kind of like aha moments that clarify how we get that selectivity, the regioselectivity. So we're focusing on the sigma complex because the key is to make that sigma complex happy, all right, for each of the 3 outcomes. All right, so remember that when we have this mixture of FeBr2 and FeBr3, that's in one pot, that makes a complex ion. All right, so we have that. And that's actually our electrophile. And so we can have that react in a number of ways. And let's show that in the ortho, meta, and para cases. So I'm going to do, let's see, I have para as my first one. So I'll do para first. So I need to pick a bond that's going to give me para. So I can't do this one. This pi bond cannot attack. It can't be our nucleophile because neither one of its carbons would occupy the para position. This is the only one that I could use because this one's not at the para position either. This is the para position. The pi bond that's part of the carbon at the para position is here. So that's one I could use to show what happens in the para case. So let's do that. I'm going to use a bunch of different colors, so I'm just going to actually start with black. So it's going to look like this, remember? We attack and we kick off. So that first step is always going to be the same. But depending on which bond I use and which carbon it goes on, it'll look a little different. All right, so we have the para position. I'm just going to write methyl, Me, that way. Notice that I left this bond alone and this bond alone. I used the para position to attach the new bromine. That means the other carbon that was part of this pi bond gets the positive charge. So now I get to do the resonance structures here. So we will delocalize around the ring, push the electrons to fill that open octet that's on carbon. So then I get the next part of the sigma complex. Now keep going. I'm going to go around from the outside just because I have a little more space there, but I could have pushed it from the inside of the ring too. Okay, so I've let every carbon that can have a positive charge have one. I want you to notice something. take a step back and decide, since we don't have, every carbon's not the same. One carbon has a methyl on it. Do we have any carbons that are happier than the others? In other words, did that methyl make a difference at all? So in other words, I'm looking at what's, oops. So secondary carbocation. Whoa, tertiary carbocation, secondary carbocation. So this is actually a big deal. This determined the outcome. Lo and behold, that is why we have the para product in greater proportion. So I'm going to draw our wow emoji, maybe. This is kind of the aha moment you get in a mechanism. So tertiary, just so we can really remember that, carbocation. So when we use that para-pi bond as a nucleophile, in order to install the electrophile at the para position, we are able to get a stabilized, I wouldn't say completely stable, but a more stabilized sigma complex. So definitely favorable to go that route. We noticed that ortho and para go hand in hand. They were nearly 50-50. So let's look at that as well. So after para, actually I have meta next, so I'm going to do meta. So I'll put my electrophile over here, Br plus, FeBr3 minus, and then for meta, I think I'll do that in green. So at the meta position, I need to pick, so here's ortho meta or ortho meta. I could pick either one of these, but just for the sake of demonstration, I will pick one. Oops, I'm kind of off the screen a little. Let me scroll that down. I'm going to pick one that's, so once again, these are my two meta positions. I could use either one of those because they both have a pi bond on the metacarbon. It will make no difference which one I choose. You may want to do both and prove that to yourself. But since I've already demonstrated what happens when I use that bond, I'll use this bond. So I'm going to use that to attack the meta, for the metacarbon, to attack the bromine. Okay, so now that's why I'm using the green arrow, just so we can kind of keep track of what's going on, that same thing. But I'll go back to red arrows for the middle. I think it's a little easier to see. Okay, so my methyl is here still. This bond didn't change. This bond didn't change this time. Now it's this one that is gone. That pi bond's gone. We need to draw bromine at the meta position. That means the other carbon of the pi bond gets the positive charge, and now we start delocalizing. That was actually the hardest part. The rest should actually be simple if you practice your resonance enough in previous classes. So move that those pi bonds around, move the electrons around, and then we'll stop and evaluate. Keep those things meta. Oh, I forgot to draw my positive charge in the middle one. So right down there. Okay, that covers it. Okay, so let's label our carbocations. Secondary carbocation, secondary carbocation, secondary carbocation. So in other words, the meta route did not give us that extra stabilization that the para route was able to do. So notice that we had secondary carbocation here, secondary carbocation here, but we had that nice tertiary one right there. So no stabilization gained from opting for the meta position. I guess we should expect to see some stabilization for ortho because it forms in a 50-50 mixture roughly with para. Let's show that here. I'm going to redraw my electrophile. We're starting from that point in the mechanism. Okay, so who is ortho to methyl? here's my methyl, ortho here or ortho here. Now I haven't used that bond yet, but I have used that bond. And I've already shown what it looks like attacking using two different bonds. So I'm going to show what it looks like attacking from the same bond. So I'm going to intentionally use this one because I've used it already, just because sometimes that can be a little trippy looking if you're not used to recognizing that one carbon gets the electrophile, the other one gets the positive charge. So let's attack. Let's do blue for ortho. Here it comes. Ortho carbon attacks bromine, and it lands on the ortho carbon this time. So here's methyl. This pi bond and this pi bond were unaffected by that change. Ortho carbon gets bromine. Other carbon of the pi bond gets the positive charge. Here begins my resonance series for the sigma complex. Start pushing it around. And keep those ortho positions, Br, methyl. This one stayed the same, that stayed the same, and now we have the positive charge here. Delocalize one last time. So we move that one over. Okay, so we kept this one the same, moved this one this time, which means that this carbon gets the positive charge. And there we have it. There's our tertiary carbocation. Might even circle this in red. Big deal. So it deserves another emoji if you want to draw it there. Squeeze that up out of the way. Tertiary carbocation. So really the moral of the story is that ortho and para can stabilize the sigma complex because you were able to get a carbocation to land on a carbon that has that electron donating group. And that's if it's an electron donating group. So what if it's an electron withdrawing group? Can it be? Yes. Then the opposite's true. How can we keep that straight? We will revisit the list of electron withdrawing groups and electron donating groups in a minute, but for now we're going to summarize it in the general template on the next page. Here we are. This is a very generic version of what we were presented with before. Remember when Z was methyl? So let's make it super generic so we can use it for anything now. So if Z is electron donating like methyl was, we expect ortho and para products to be distributed. All right, so if Z is an electron donating group, then the ortho-para sigma complex carbocation is stabilized. Therefore, the major product is the ortho-para products. What if Z is electron withdrawing? Okay, so this would be Z equals EDG, so E plus is our electrophile, Z equals EWG. Well, remember our sigma complex. Remember in our sigma complex, the reason that we chose to go ortho and para as major previously was because a carbocation landed here and Z helped it, stabilized it, it made it tertiary, right? Or it could even, in other cases, give it resonance, which is even better. What if it's an electron withdrawing group where it makes it instead of alleviating the positive charge, it pulls electron density away from it, which is the last thing a carbocation wants? That destabilizes it. So if we're going to destabilize it, then it does not want to be there. And that means Z doesn't help it, it actually hurts it. So then it would avoid landing on the ortho or para positions so that it would not have that destabilizing effect. In those cases, when we have that electron withdrawing group, then we get the meta product as favored. So it's not that the meta is ever bad or good. When we go back to let's do that, let's just take a quick look. Notice how the meta didn't really do anything for us. It's always secondary That's because the carbocation never landed on the carbon that had the substituent. Whereas the ortho and parasigma complexes, the carbocation always landed on a carbon with a substituent. In the case of toluene, methyl was a good substituent for the carbocation. It's electron donating. Remember by hyperconjugation that methyls are weakly electron donating. So if this is a weakly electron donating, it's going to stabilize that carbocation. If we have the opposite case where this is an electron withdrawing group, we place methyl with an electron withdrawing group like a carbonyl or a nitro group, something like that, then we would take away electron density from the carbocation, make it a bigger effective charge, which is destabilizing. Remember, we always strive for neutral electron distribution. So in that scenario, para and ortho would be avoided, and meta would be like just the default option available because it does not get destabilized. Okay, so you got to look at what you got and make a judgment call from there. It all depends on what's attached to begin with, not what you're adding, what's actually attached. Okay, so let's finish that up. Then the major product is meta. Okay, more effects from now that we've dived into substituted benzenes. Before we get into tri-substituted, we need to really fully understand what it means when a benzene's substituted. What does that have as an effect on the reaction rate as well? So it doesn't just change where things go, it also changes how fast the reaction goes. So let's consider we're doing two reactions side by side and we're going to have a little competition. Benzene is in here. So we've got benzene versus toluene. And we're going to try to brominate both of them. The question for you is who wins? Who reacts first? We start the clock at the same time. We give them the same amount of reagent, apply the same amount of heat. Who wins? In other words, who finishes the reaction first? And because they're not the same molecule, there is a right answer. There's going to be one that finishes first. And I'll give you the answer first. It's going to be toluene. Why is that? Well, let's draw the possible products first. With benzene, when we do a bromination, we're going to get the mono-bromobenzene. When toluene, we can get, remember that we just did this one with the mechanism, ortho, because carbon is electron donating weakly, at least we'll get the ortho and the para. Oh, that's a really terrible hexagon. There we go. And where was my methyl? I put it here. I'm going to put para. All right, so what is going on? What's the difference? Remember, it all goes back to what we actually just talked about. The sigma complex is stabilized by the methyl's electron donating ability, hyperconjugation in this case. So methyl stabilizes the carbocation in the sigma complex. Well, guess what? Carbocations are rate determining steps, i.e. you can make the carbocation more stable. That's the faster reaction. Okay, so the one with toluene is faster. So methyl is what we would define as an electron donating group, which we have before, but H is in the middle. It's neither electron donating nor electron withdrawing. It's our baseline, our reference point. So anything that donates more electrons than H is electron donating. Anything that withdraws more electrons than H is electron withdrawing. So to sum this up, when donating electrons, that makes the benzene ring more electron rich, which means it's more nucleophilic, stronger nucleophile. Stronger nucleophiles react faster. When it donates electrons, it helps make the carbocation more stable. So that's a double whammy, right? So we could say, if it makes the ring more nucleophilic, a synonym for that would be to say It activated the ring. So if something's just kind of blah, lazy, like we could say benzene is, you put a methyl on it, we might say it's more hot or activated, ready to go, ready to react. So activates it. All right, so because methyl makes the reaction actually happen faster, so if a reaction's measured and it actually happens faster than it would with just benzene alone, benzene H's alone, then we say the term for that is that it did indeed activate the reaction. Other activators are usually other electron withdrawing groups. Donating groups. So how do we spot one? We're not going to memorize every electron donating group in the world. We're going to recognize a list that I'll provide you, but with enough practice, you'll just kind of spot them quickly. But what if we saw one out of the blue that we didn't recognize in the future? How would we know to guess which category it fell into? So there's some traits that are important to note to distinguish an activator from a deactivator. An activator can donate electrons. So it has an ability to donate electrons in some way. How can it do that? That might be by hyperconjugation, which an alkyl group can do. But an even stronger dominating effect would be resonance. What do you need for resonance? Sometimes you need a lone pair nearby, right? Pi bond. Okay, so keep that in mind. Okay, so when something is an activator, it's usually a sign that you have electron donating ability. It makes the pi bonds in the benzene ring more reactive because they're already electron rich to begin with, so they're more electron rich. Orthoparadirectors stabilize a carbocation, right? So why are we using two different words? Why don't we just say, oh, what's our list of orthoparadirectors? What's our list of activators? And it turns out there will be a distinction. So let's go find out the difference. In reality, they overlap most of the time. There's only one exception we're just going to have to handle, and that's what we'll handle the exception first, get it out of the way, and then the extremes will fall really nicely into their categories. Okay, let's do another race. Identify the faster reaction. Anisole reacts with bromine versus chlorobenzene in bromination conditions. Who's going to be done first? Well, we know that they both have lone pairs on the O. We talked about lone pairs. They're not alkyl groups. There's no hyperconjugation. So we have to know, are these activators or orthoparadirectors, right? So notice what we could do with that lone pair. We can literally donate, that's even more pronounced of an effect than hyperconjugation, which is what the alkyl groups could do. We can literally donate some electron density in, showing it with those arrows. We can draw resonance structures, and I'm not going to do it all here, but that arrow shows that I could do that and start opening up the pi bond and show that the ring is literally getting more electron rich thanks to that lone pair nearby. It's pushed toward the ring. Therefore, this whole ring is more electron rich than if that ether was not present. Therefore, we can call this an electron donating group. So resonance tells us it's electron donating. Therefore, it makes it more electron rich, therefore it's activating. Okay, activating means the ring is more electron rich. Now, what happens in the sigma complex? Let's visualize that mechanism. Remember that the carbocation lands here on the carbon adjacent to the group if we were going to let it go orthopara. So I'm going to always ask that question, can it be orthopara? That means, does this help that carbocation if it goes here? Okay, so that's how I usually solve it first, is I kind of let it pass a test. Can it be orthopara? Would it be happy being orthopara? So in other words, if there was a carbocation here, And I'm not keeping it there, by the way, so don't get that in pen. But if there was a carbocation in there, would it be happy? Why, yes. It's actually extra happy. There's resonance. I could push that arrow down and fill that open octet and delocalize it not just with around the ring, but even outside the ring. So this is secondary with resonance. That's a very stable carbocation. Therefore, yes, I make the carbocation happy here. Therefore, yes, orthopara is preferred. So I'm going to undo my carbocation because I'm trying to draw the final product. What I might do is keep it as a reminder. Right? So that's just one of the, that's like the key one out of the sigma complex that we have to extract from the mechanism. So therefore, since secondary with resonance, therefore orthopara preferred. So that makes it an orthopara director. I'm at OME since I got a little squished there. So I'll draw my para plus my ortho product. All right, so I'm going to move some stuff out of the way a little bit. And I'm also going to add a few more notes to summarize what we saw here. It's an activator. So OR groups in general, right, is an activator and orthopara director. So activating, when we prove that it's an activator, it means it speeds up the reaction. It goes fast. Okay. Now, halogens. They look like they should have the same behavior, lone pairs, and in some ways they do. But it's just, we'll see very soon when we rank all our groups, there's a spectrum we're establishing. And we can't make it binary in science. We can't say it is or it isn't at all times, because when it's in between, it sometimes satisfies both conditions, and it's going to actually have both labels. So at the end of the extreme, we have activator orthopara director. At the other end of the extreme, we have deactivator and meta director. But in the middle, we have the halogens. They're the exception. They're the ones that will cause you a little bit of a headache. But we'll try to understand why they're an exception and why they fall in the middle of the spectrum when they at first look a little, they look more innocent than that. Okay, so what's going on here? The halogens are going to give us they're not actually considered, like if we actually do the reaction, so let me go back here, excuse me. I asked two questions. I want to answer this one first. The faster reaction. So we talked about the extreme ends. So this is the faster one. And how did I determine the fastest reaction? Once I'm able to determine something's an activator. So this is, OR groups are strong electron donators. Halogens actually go slower in a reaction than benzene alone. That means they're actually withdrawing electron density. So that means by the inductive effect, halogens actually look more like this. Electron density is being pulled away. Deactivates. However, there is a resonance structure we could draw with the lone pair. Okay, and that makes it electron donating by resonance. But when the experiment is actually performed, so our prediction would be like, we have a dipole, strong dipole, suggesting that the inductive effect tells us it's electron withdrawing, which you could do, by the way, here as well. However, when we draw resonance, we don't see that resonance very often. Chlorine doesn't really like to make that pi bond, whereas oxygen doesn't have such a problem accommodating that, right? We've done that many times. And there's a couple reasons for that. So, and we'll dive deeper into that once and for all. So why is the resonance usually wins and dominates inductive effects, but in this case it doesn't. So the moral of the story is it's still considered electron donating enough to stabilize this sort of sigma complex. So in other words, when we get to our sigma complex here, and I'm going to skip to the aha sigma complex, the eureka moment. It's electron donating just enough to stabilize it. So we'll stabilize this. However, it's still a slower reaction, which indicates that the ring itself has been deactivated. It's slower to, so it's two discrete things going on here. This pi bond was slower to attack, right? Slower to attack than this one. That means that it's not as electron rich, thanks to this inductive effect. So we still get orthopara because the carbocation stabilized. So that's good news. It's simple enough to say, hey, when I want to know just my products, I have to ask, did this help or hurt the carbocation? Helped it. So let's draw it. Bromine and chlorine. Ortho. And, oops, I forgot the pi bond up there. Para. However, I'm going to write a note up here. This one was the slowest reaction. So in other words, I'll write this in green. It was still an orthopara director, but it was a weak deactivator. Weakly deactivates. Okay, so this is always a point of confusion. You could, of course, memorize this tidbit, but it's going to stick with you a lot better if we get to the bottom of why. And to be honest, the arrows, the mechanism usually tells us why. But our arrows are the same. So we could have drawn this dipole here as well. So when the arrows are the same and the mechanism arrow pushing alone is not giving us the full story, and that's actually, believe it or not, that's not as deep as we can go. We're trying to simplify things with the mechanism to avoid going too deep every time. But when the mechanism doesn't tell the whole story, we have to get to the orbitals. Orbitals are finally going to tell you what's going on. So we're going to devote a little time to that. Exceptions are sometimes annoying, but they're also really interesting. We like to know why things didn't follow a rule that we see everything else follow. Why is that so special? So we're going to kind of work this out. Okay, we're going to show the two effects that the halogens have on the benzene ring and how they actually conflict with each other. So we have the resonance effect. And that can actually move the pi bond around the ring, right? So that's contributing electron density. So I'm going to define that right here in a few more words. So I'm going to say that activates ring by, so donates electron density to the ring, right? Overlapping of p orbital. That's the definition of the resonance effect for how it can activate a ring. You have to have, in order to have the resonance, you have to have the p orbitals overlap, right? Okay, so inductive effects, they do the opposite. If X is electron withdrawing, which it is considered because it's so electronegative. So notice that we have the dipole going this way. So the inductive effect, why don't I do it in blue since the text is in blue? All right, the inductive effect deactivates the ring. Deactivates ring because halogens are so electronegative and pull electron density out. So in other words, we have a tug of war going on. We have a push from the electrons for resonance, and we have a pull from the polar bond, the dipole moment. Who wins? Usually resonance, because resonance literally moves and delocalizes the electrons, whereas inductive just kind of distorts the cloud. However, in this case, the resonance is not as effective as normal. Let's see why. Remember, what we need for the resonance effect to be effective, to actually be useful, is to have our p orbitals overlap. Now, these are what the carbon p orbitals look like in the ring. Nice orbital overlap would be a substituent has the same size p orbital that can nicely overlap. So let's indicate that with show that overlap. Once you change the size, you get a mismatch. You get very poor chance of overlap. Why would we change the orbital size? This goes way back to fundamental general chemistry. What happens is you go down. We've been staying in, actually I remember this being a point that kind of blew my mind for a while when I was in organic chemistry, because we stay so long in that second row that we forget what's in the other rows. And if we look at all the halogens that are attached here, so let me just draw them in. Let's say this is fluorine, chlorine, bromine. These are some of our favorite ones to use all the time. Fluorine is the only one that matches the size of chlorine, but it's so ridiculously electronegative. It's the most electronegative atom on the periodic table that we can't possibly compete with that even in a resonance situation. So best orbital overlap, however, huge dipole. The dipole gets smaller as we go this way, right? And it's pretty much non-existent by CI. However, look at the very poor orbital overlap. So in other words, the trend we're really observing here is as you increase orbital size, you decrease orbital overlap. And you need that orbital overlap in order for resonance to happen. So halogens are kind of at that sweet spot because we go across the periodic table. We're sharing carbon, oxygen share a row. So does nitrogen. Remember Funkel, O, N, C, F. Those are all in the same row. But as soon as we get down to chlorine, bromine, iodine, we're not in the same row anymore. Sulfur, by the way, has the same problem. So we're not in the same row, then they're going to have different orbital sizes and the orbital overlap suffers. And that will actually dictate how effective resonance can actually be. And pi bond formation and other features, we'll see that come up to play. Okay, so I summarized that all here, don't worry. So let's just fill in the blanks so that we have conceptually that down. The only atom that has a similar size p orbital is C is F, since they only share a row. However, F is so electronegative, which I abbreviate EN, if you want to write that out, that the inductive effect ends up dominating. And it deactivates the ring, right? Note, chlorine, bromine, iodine are third, fourth, fifth rows of the periodic table. So resulting in poor orbital overlap. That lessens the contribution of resonance to electron density of the ring. However, the resonance contribution exists. It's not completely a wash. It exists just enough to do its job here. Stabilize the sigma complex. To stabilize the sigma complex in the transition states. Thus, it is still an orthopara director, yet a deactivating group. It's the only one that is one of each. Okay, I know that's brainful, but I think when we've worked at the top where we have the activator electron donating group. Then we have the deactivator, but still ortho-pair director. We're going to go to the bottom where we have electron withdrawing group, meta director, deactivator. So don't worry, that's actually more obvious. So what does that look like? When we have an electron withdrawing group, we will want to use the whole Lewis structure. So the mechanism helps a lot. So draw out nitro, looks like this, has a hidden Zwitter ion in there. You'll want to draw it out because this is in the chapter where we do nitration. So draw out your nitros. All right, so you might have guessed it if you remember that nitro is in one of our classic electron withdrawing groups that we've used in the past. It's going to be, let's see, O2N, because we always draw it as attached at the end, the meta product only. Okay, because that's an electron withdrawing group. Let's prove it. Prove that it's electron withdrawing. Prove that it's not going to help the sigma complex, in other words. The rate determining step is that sigma complex. I'm only going to draw now, to keep this even simpler, I'm going to skip straight to the sigma complex.